In this screencast, I'm going to show you the basics of the golden section search method. So this is really similar to the bisection technique, but instead of finding the zero of a function, we're actually trying to find the minimum. So if we have a function here, f of x, and we have an interval here, a to b, and we know that there's a minimum. Oftentimes you might not know what this looks like, you might not have a plot of it, but I'm going to show you the general idea of trying to find the minimum. Obviously the minimum here lies, somewhere, let's just say in this region, but we don't know the minimum. So the golden section search method is a pretty unique and interesting way to find the minimum. We start out with bounds. So just like the bisection technique, we have an a and a b that we choose on some interval. We want to find the minimum in that interval. We then compute something known as d, and that's equal to square root of 5 minus 1 divided by 2 times the interval length, b minus a. This number here, root 5 minus 1 over 2, is something known as the golden ratio, which is about 0.618. It's found in a lot of things in nature, and it makes this technique work pretty well. Once we have calculated d, we go in here and we want to compute two values. We want to compute x1 and x2 as shown here. Now x1 is just a distance d away from a. So this distance here is just d. So x1 equals a plus d. x2, on the other hand, is d away from b. Okay, so that's d as well, but it's down from b, so you have to x2 is equal to b minus d. The next step in the golden search method is to actually calculate the function values of x1 and x2. So we want to calculate the function values here and here. And let's just say in this example, f of x1 we find to be less than f of x2, right? As shown here. What that means is that since f of x1 is less than f of x2, we know that the minimum cannot be here on the left. So the minimum cannot be here because we found that the function value at x1 is less than x2. However, it still might be found over to the right of x1. But for this particular step, we will actually eliminate everything to the left of x2. And then the final step of this iteration is to redefine x2 is now going to be our new a. So the lower bound of our interval. B is still going to be the same. We're not doing anything with that, similar to the bisection technique. And then with this technique we can actually name, because of the mathematics of this, we're going to rename x1 to be the new x2. So new x2 new is equal to x1 old. Okay? And when we do that, then, because we've renamed x2 as a and x1 as the new x2, we're actually going to have to calculate a new, in this remaining bound, a new x2. Okay? So it's a little bit differently if we would have found f of x2 less than f of x1, because then we would have eliminated stuff to the right of x1. And then you would actually rename x1 to be the new b, and the new x1 would be the old x2, and then we have to calculate a new x2. Alright, So let me show you what this looks like with an example. So I've got a function here, y equals x squared minus 6x plus 15, and I'm going to choose my interval to work with is going to be we have 0 as our a and 10 as b. So again, the first step is calculating, after you know b and a, is to calculate d, which is just the golden ratio, times, so this is our golden ratio, times b minus a. So x1 again is given by a plus d, x2 is b minus d, and when we do that, for this particular case, d is equal to 0.618 times 10, because our b minus a is 10, and that's just about 6.2. And x1 then is a plus d. Because a is 0, x1 is just going to be about 6.2. Now we compute x2, and that's b minus d, and for this example that's 3.8. The next step is to calculate the function values. So we want to calculate the f of x1 and f of x2. So f of x1 is there, f of x2 is here, and what we find in this particular case is that the function at x1 is greater than the function at x2. What this means is we can completely eliminate everything to the right of x1, because we know that the minimum can't lie to the right of x1 because we found something already that's less than f of x1. Okay, and when using this technique, the x1 becomes the new b, so it's going to be our upper bound, and x2 becomes the new x1. So now we're going to zoom in on this region, 0 to 6.2, and here we have drawn that. And again, we don't need to recalculate x1 nor b because we're just using x1 as the previous x2 and b is the old x1. So next step, calculate the new x2, which is b minus d. So for here we have 6.2 minus 3.8. We now have a new d because we now have a new interval, and x2 is equal to 2.4. We now calculate the function values, and you can't really tell with this example, but f of x1 is just slightly greater than f of x2. So what we'll do is similar to the previous example where we remove everything to the right of x1. x1 becomes the new b, the upper bound. x2 becomes the new x1. We can then zoom in on 0 to 3.8. We don't have to recalculate x1 because that's the old x2. We don't have to recalculate b because that's the old x1. But then we can calculate a new d, which is about 2.4. We then calculate a new x2, about 1.4, and we keep going. We calculate the function values. So in this case, f of x1 is less than f of x2. In the other two iterations, it was actually greater than. So in this case, we're going to eliminate everything to the left of x2 because we know that the function, the minimum, cannot lie to the left of x2. And in this case, the new x2 is the old x1, so x1 becomes the new x2, and x2 becomes the new lower bound, which is a. And then in the next iteration, we would have to calculate a new x2. So we'd have an x2 somewhere in here, and we keep going until we zero in on the actual minimum.